Hello! In this Mathematica tutorial, I'm going to start from the very beginning and go through and do some of this very elementary stuff in the beginning of the booklet. So if that's not what you're looking for, then go ahead and find one of my other more advanced videos. But this one's going to be about the very basics, so the very beginning things in mathematics that you would want to learn if you're starting out in learning about maths. Okay, and that is preparatory math. So let's just get straight into it. So sets. These are very important in mathematics. They are collections of usually numbers, but they can be other things, including sets themselves. So they're collections. Now, they can contain they can contain numbers, they can contain empty sets, but what you don't want in them is duplicates, okay? Whereas with an array in Mathematica, you may have duplicates. So because this is a Mathematica tutorial, I'm doing an elementary discussion. Well, why don't we open up a Mathematica notebook? Okay, now let's see, file new, notebook, bring it over here, go window, magnification 300 so we can all see. Okay, so look, you can enter some of these as arrays. Okay, so I'll say A equals 1, 2, 3. Okay, and I'll put, actually, let's not leave a semicolon, shift enter, and then it gives it right back to me. Okay, now it knows this as an array, meaning just a list of numbers that can have duplicates. But if, let's see, if we call lowercase a union, we use a built-in function called union uppercase A. Well, it looks the same, you see, but in doing that, you get rid of the duplicates and you can calculate these as if they were sets. Calculate with them. Okay, so now that we understand that, let's come down here and enter B equals -2, 5, and 11. All right, and we'll say lowercase b equals union uppercase B. Now, you know what? This is not going to do anything but give us back this right here, okay? So why don't we just change this for the sake of this exercise and include -2. Right? So I've entered an array there, but if I want to think about this as a set, then I don't want the duplicates in there. Okay, so if I use union for that, it's omitted the duplicate -2. Okay, now let's see. We may as well just enter the last one, but C in Mathematica is protected. So let's see. Can we see what C is? No. Okay. What about a numerical value of C? No. Anyway, C is protected. Okay, so let's call it something else. Let's call it G. That looks a little bit like C. So we have 0, 4, 8, and -3.6. Now, let's, while we're at it, observe that the numbers in A and B were whole numbers, whereas the numbers in the set C are not all whole numbers. In fact, this -3.6 is a negative decimal number, which is not whole. Okay, you can view it as a fraction if you want to, so you can call it rational. All right, but they're not all whole numbers. Now, you don't have to, in order to call something a set, have all the same kinds of numbers. Okay, but when you do, you might refer to them excuse me, with certain symbols. All right, let's scroll down and I'll show you some examples. In this table here, So this symbol right here, it's like a 0 with a slash through it, okay? That's the empty set, or the set with nothing in it. Right, that's an important set. Empty set. Okay, then there's another set known as the natural numbers. So these are the counting numbers, 1, 2, 3, etc., 4, 5, 6, and on and on and on. All right, there are infinitely many of these counting numbers, and they're called natural numbers. Okay, but when you incorporate extra elements, the negatives and 0, into your collection, all right, you extend the natural numbers to negatives and 0. Well, we call this the integers, and we have a symbol for that. It's double struck Z. Okay, so why these symbols? Well, back in the day, around the 70s, when it became cheaper to use typewriters for typing rather than, I guess what they did is make special symbols and stamp them. I don't know. But around the 70s, it became economical to use typewriters, right? But how do we distinguish that we mean integers? I think that's a Z for Zahlen, integers in German, okay? But the way you would do this, make a bold letter, because these were originally bold letters, is you would take the typewriter and write the same letter over the top a little bit, and you'd get something that looked like this. Now, apparently that became a symbol that most of us would associate with these sets. And so these days we try to make it look a bit like that. And so we have these special symbols for these particular sets. All right, now the next one is the rational numbers. Rational numbers, it's a double struck Q. All right, you can have positives and negatives, but it's the collection of all fractions. Okay, and there's some examples. Rational numbers. Okay, what about real numbers? So real numbers are all of the numbers in between the fractions. Okay, so that seems a little bit, well, over your head maybe, but basically between any two real numbers, there should be another real number. All right, so you might think of these as numbers with long decimal expansions, for example, pi, or e, or the square root of 2, 1.4142, 13562, etc. But if I take any two integers, I can find a real number between them. Right? For example, just look at these two, -1 and -2. What would be a number between those two? Well, there are no integers between those two numbers, but there are definitely, well, infinitely many rational numbers between those. But between what you could imagine as the closest two rational numbers to one another, you can find a real number. All right, so think of real numbers as a continuum, right? And the best way to think of this is with a line. Right, now if we scroll down, I know I've got a picture of a line down here. Okay, this is the number line. So if you look at this, this is a line here. Every point on this line can be associated with a number whose distance, it has a distance from 0, right? So any here on the right of the number 0, any point on this line, I can just randomly pick one right here, okay? And where I stop my mouse, there is a distance from that point to 0, okay? And that distance is a real number. All right, so, and also on the left of 0, we've got negative real numbers. It's very handy to be able to think of real numbers geometrically in this way, right? So where, you ask yourself, is the number pi? All right, pi is 3.14159262525, etc. Okay, it's not rational, but if we think of it as around about 3.1, well, that puts it just a little bit to the right of the number 3. My head's in the way, a little bit right of the number 3, right about there. Okay, and we can think of it geometrically on this number line. Okay, as in it's greater than 3 because it's to the right of that. Okay, it's greater than 2 and so on. It gives us a way to think of, to orient our thoughts about real numbers. Okay, all right, so let's scroll back up and talk about this other stuff. Okay, complex numbers. Now, to think about complex numbers, you need to know about imaginary numbers. All right, so many people will teach you in maybe primary school or something that you can't take the square root of -1. That is just absolute bogus. You can, it's just not real. Okay, it's not real in the sense that it doesn't fit on the real number line, just as I described below. It's a complex number, and more specifically, the square root of -1 is an imaginary number. And so all we do in mathematics, we just use the letter I to denote it. Okay, and we say that I squared is -1, and we just leave it at that, more or less. But now if you want to talk about numbers that include real numbers together with an imaginary part, well, they're complex numbers, and we can fit those on a two-dimensional graph. So we can think of those geometrically too. You know, here's my two-dimensional axes in a two-dimensional plane. Okay, and on that plane I can find, say, let's just choose a complex number, and I'll think about this in terms with Mathematica, okay, because I'm describing this and I'm also going to be able to do this in Mathematica. So in Mathematica you use an uppercase I to denote this. Okay, so let's just try squaring that. I squared. Okay, you get -1 when you press Shift Enter. Now, what I'm trying to tell you is that there's a way to think of these geometrically. So if we just say, well, consider 2.5 plus 3i. All right, that is a complex number. It has a real part 2.5, an imaginary part 3. Okay, so the sum of those two is complex. It's an example. Right, in comment form, example of a complex number. All right, and now let's think of this complex number in the plane. All right, when you do that, you want to associate that with a point. Okay, so let's write associate with the point, and I'll use the curly brackets for this, 2.5 and 3. Okay, so there's a point, the point 2.53, which lives in a plane, you see. Now, the real part you want to put on the horizontal axis, and the imaginary part, in our case 3, goes on the vertical axis. Okay, so let's plot this in Mathematica. All right, but in order to have a frame of reference, let's also plot the point 0, 0, as in the origin. So I'll write, let's see, what do I want to write? Let's just go list plot. That'll be the easiest. List plot. Okay, and I'll put in 0, 0, and then this other point, 2.5, comma 3. Okay, if I list plot that, I think I'll get a couple of small points. Well, they're big enough that we can see them. All right, so here they are. Here's 0, 0, which we just put there for reference. And then over here, we've got the point 2.53. Now, if you view this horizontal line here as the real number line, well, you see this is not on the real number line, is it? It lives up higher in a complex plane. All right, it has real part 2.5 and imaginary part 3.0. And so if we want to view this complex point geometrically, we can do that. We just put it over here. Okay, So that's great. It's very helpful to be able to think of numbers geometrically. Okay, so I'll move this over and then I'll scroll down and see what else I have to tell you on this page. All right, so we've got some important symbols used to discuss sets. All right, I've put those in a table. Mostly, this is just a very abbreviated collection of key ideas in basic mathematics that's in this booklet called a YouTube course in Mathematica. All right, so let's have a look. Now over here in the left column, I've got some symbols that you might run into when you're dealing with sets. And then this is what they mean, and here are some examples. Okay, now this one, some of my students in the past have had some questions. What is this symbol? Right? Even after you define it and start using it, someone asks, what is it? Okay, that's fine. It means this belongs to. Okay, so let's have a look at the example. 2 belongs to the set 1, 2, 3. This is a finite set, has finitely many elements in it, 1, 2, and 3, and 2 is in it. Okay, so 2 is a member of, 2 is in, 2 belongs to. There are a number of ways to say that. Okay, so have a look at this next symbol. This one means 2, it does not belong to. Okay, so if you put a line through, now that's common in maths, if you put a little slanted line through it, it means not that thing. Okay, does not belong to. For example, 8 does not belong to the set containing 1, 2, and 3. All right, so for all, this is looks like an upside down A, but it's probably not. Okay, for all x belonging to the real numbers, x squared is greater or equal to 0. That's what that says. Now that's an abbreviated way of saying just what I said in English. Okay, you don't generally want to use these symbols unless you are dealing with sets or logic. Okay, they tend to be reserved for sets or logic. Having said that, when you're in a mathematics lecture, you might see people using this when they're describing things other than sets or logic. Okay, that's because, you know, it takes a lot of effort to write on the board in English in full sentences when you've also got to talk about it. Okay, so sometimes it's easy to talk about it using these symbols. Okay, so this one means for all, and that's a true statement, right? All right, this one that looks like an uppercase backwards E means there exists. Okay, so you can say that as there exists a real number x such that x is greater than 4. Now, as a personal preference, I prefer not to use this vertical bar here to mean such that. I would prefer to use a colon, okay, as in the 2 dots on top of each other, because if you're dealing with elementary number theory, this symbol also means divides, okay? And I don't like ambiguity, so I tend not to use this to mean such that. However, it's very common to use a vertical bar to mean such that. So we'll go with it here. All right, now this symbol means there does not exist. Okay, there is no x belonging to the real numbers, or there is no real number such that x squared is negative. True, okay? This means implies. Okay, so if this, then this. All right, which is the same as implies. For example, x is an integer and it's positive means that x is a natural number, okay, a counting number. True. All right, this one right here, it's got the arrows going both ways, and sometimes we'll abbreviate this with an IFF, okay, means if and only if, or these two are abbreviate if and only if. X is an integer and positive if and only if x is a whole number. A natural number, and the counting numbers. All right, subset is a subset of. Okay, so the set containing 1, 2, and 3 is a subset of the set containing 1, 2, 3, and 4. And that is also a subset of the natural numbers. Okay, next one is a subset or is equal to. So the set 1, 2, 3 is a subset or equal to the set 1, 2, 3. In fact, they're equal. Okay, two sets are equal if and only if they contain precisely the same elements. Union. So in Mathematica, I showed you union earlier. All right, so I'll bring it back up. This union. Okay, union, I can apply that to an array to get a set, or I could apply that to two sets, and what it does is it just joins the elements. Okay, and you don't have the duplicates, so let's just try that with these two. All right, so I'll say union of A and B, shift enter, and we'll scroll down and see what we have. So this right here is the union of A and B. Okay, it's taken the elements of each, put them into one set, and thrown out the duplicates. Okay, then we have intersection. So let's look at this in Mathematica, and I'll put semicolons after these. Okay, so we'll keep union shown. Intersection of A and B. All right, let's think about this. If we're looking at what A and B are, what do they have in common? That's the intersection. Which elements do they have in common, or the collection of all common elements? Now, in these two, I don't see any common elements, so the intersection should be empty, as in the empty set. Okay, shift enter. Let's have a look. Yes, it's the empty set. So the intersection of A and B is empty in that case. All right, so intersection of. So the intersection of -1, 0, 1, 2, 3 with the set of natural numbers that is greater than 1. Well, that is just the set 1, 2, 3, right? We can do that in our head. Okay, now finally, we have this symbol. It looks like times, right? So if you're using this with two numbers, well, then you probably mean multiplication. If you're using it with two vectors, then you probably mean the cross product. But if you're using this with two sets, well, then you probably mean the Cartesian product, which basically means the set of pairs taking one from each. Okay, so for example, the Cartesian product of the sets 1, 2 and -7, 2, well, you see we take the 1 and we pair it with a -7, and we get this pair 1 -7. And we take the 1 and we pair it with the 2, and we get 1, 2. All right, now we take the 2, we pair it with the -7, we get the point. 2 -7, finally 2 can go with 2, and we get 2, 2. All right, that's the Cartesian product. All right, so we've talked about the number line. So finally, I think we'll just talk about intervals, and then we'll wrap it up. Okay, so intervals. Well, the best way to think about intervals is with the number line. All right, so these are subsets of the number line, or the real numbers. Okay, now the closed brackets, all right, for example, closed brackets, square brackets, this means to include the endpoints, right? For example, the set of all real numbers between 1 and 3 inclusive, all right, you would write square bracket 1, 3 square bracket, okay, and we'd call that closed. Open intervals, or half open, half closed. All right, let's talk about open first. All right, open, we use a round bracket. All right, so down here is an example. The set of all real numbers between -1 and 1, but not including those endpoints. Okay, so 1 and -1 do not belong to this set. The set containing. Now you look at this and you think, well, that could denote a point, right? It's just that we've used the notation twice. So how do you know the difference? Well, through context. Okay, you note that those are different through context. So in this case, we mean to use this notation for the set of all real numbers between -1 and 1, not inclusive. Okay, with this one, well, you don't have to worry about distinguishing or disambiguating between points and intervals because it's fairly clear. Okay, -1 to 1, inclusive, to include the endpoints. The 1 belongs to this set. So that's an example of a closed interval, and this is an example of an open interval. Now you could have half open or half closed, okay? So that's when you mean to include one endpoint but not the other, or vice versa. Okay, now that's very brief, and the next topic we'll do is summation notation. All right, but that's all for now, and I'll see you next time. Thanks for watching.